Right? All right, good afternoon, everybody. Hello, everybody, and it's my pleasure today to introduce Mr. John Robie. John is a senior electrical engineer and program manager at V2X. His team primarily supports the Department of Defense through radio frequency engineering work involving spectrum sharing, electromagnetic compatibility, radar development. Mr. Robie attended Virginia Tech's a Master of Engineering program from the period 2020 to 2022. And he worked with Dr. Stavro, and they published a conference paper together. And without further ado, the floor is yours.
Thank you. Hi, everybody. Pleasure to be here. So here's my bio slide, but you guys just got it. Like he said, went to Virginia Tech for my Master's of Engineering from 2020 to 2022, part-time virtually, which personally I found to be a really, really comfortable arrangement while I continue to work full-time. I hope you guys are finding it the same. And I work out in Dahlgren, Virginia, primarily for the Department of the Navy. When I started the program here at Tech, I was a Department of the Navy civilian. I've since moved over to be a defense contractor, and it's a bunch of RF work. Today, we're going to talk about spectrum sharing and also electromagnetic compatibility, because I found that actually last year, somebody gave a really good talk on spectrum sharing, and there was a lot of overlap, but we'll get to that. I want to talk a little bit real quick about who V2X is. I have this map here of where Dahlgren, Virginia is. That is where our spectrum engineering division is based. But V2X is a global company headquartered in McLean, soon to be Reston. They primarily do base operations and maintenance. They make sure that all of the things you need to host people in a foreign base get there on time, things are working, maintenance, all of that sort of thing. And they happen to have some engineering portfolio, which we're a part of. But the part of the company I work for has been a multitude of things over the years: Centel, V2X, Vectrus, and we support activities at Dahlgren and the United States Marine Corps and Office of Naval Research and a couple other folks. So real quick, because a lot of the stuff is DoD stuff, we're not going to go super in deep to exactly what I do, but we're going to talk about the engineering behind it. I'm going to get really into the weeds, which I always liked. It's not going to be very high level. So we're going to do a quick EM refresher for folks who don't have that background necessarily, but I think a lot of you are already going to know this very well. We're going to talk about spectrum both as a resource and how we share that resource. We're going to talk about electromagnetic compatibility. And then if we still have time, I have some slides about very, very current policy documents on what sorts of spectrum research is being funded. And I think that would be worth going through even on your own time if we don't get to it. So capacity, information capacity of a noisy channel is given by this equation. Capacity is C there in bits per second. And what I want you to pay attention to is it's a product of bandwidth and signal to noise ratio. So if you want more capacity, you need more of one or either or both. Also, if you haven't had it, the Friese equation talks about how much power is received at a receiver from the power sent by a transmitter. It's a product of the power of the transmitter, the gain of the antennas on both systems, and also a product of 1/distance between the two. And then finally, we have the radar equation, which is sort of like the freeze equation, except that we are transmitting from the transmitter, propagating through the atmosphere, getting all of our spreading loss that you have in the freeze equation, other atmospheric losses, and then we reflect off of an often quite lossy target, travel all the way back in a monostatic radar to the receiver, which typically will have the same gain as the transmitter. We have that equation there. The important thing to note there is still power is a big factor, and also you follow for the range. Finally, to be able to operate your communication system or your radar, you need the received power to be above the noise floor. And noise power is given by KTB. K is Boltzmann's constant. The important ones here are your system temperature and, again, your bandwidth. So to be able to detect your signal, you need your received power to be higher than your noise power. And that's where our SNR comes in. An important figure of note is your signer rather than your SNR, which is not just signal to noise, but signal to interference plus noise. The noise is created in your receiver. The interference is created over the air and couples into your receiver, and is anything that couples in that isn't your intended signal. So when we're looking at spectrum sharing, reducing interference is a big part of the problem. So spectrum is a resource. Here are a couple of lovely plots showing roughly linear growth in value of wireless devices and a greater than linear growth in number of megabytes of traffic every year. This is just in consumer wireless traffic. So as you can see, when we have something that sure looks like exponential growth, you need somewhere to put all of it. And the metaphor I'm going to be using throughout the talk is think of the radio frequency spectrum as being just like physical land. It is, for our purposes, limited, and they don't make more of it, and you need certain amounts of it to achieve your goals and exist on the spectrum. This is a map of how we use the spectrum, and it's as big as I could make it on the slide and still not particularly readable. But suffice to say, there's about a 100-page table that explains this picture here in greater detail, with another 700 pages of reference manual to explain. So each of these little boxes here is a certain type of station or station class that is allocated to that particular portion of frequency. Frequency is here in the x-axis. All kinds of rules about how you can act, what you can be doing with the signal in that band, what kinds of interference you are allowed to get away with or should expect. And if you care about policy, or even if you don't and you work in the RF field, you're likely to encounter this and have to understand at least the ins and outs of the rules for, maybe the particular product you're making. So some of that land is more valuable than others. And one of the many reasons, one of the largest reasons is here operating on the Earth, we get not just spreading losses we propagate, but we are absorbed by the atmosphere. So I don't think my pointer shows too well, but if you're looking at the green line here, that's how much loss you get per unit distance with respect to your frequency being in the x-axis, and you see a lot lossier the higher in frequency we go. So over there on the left, if you want to propagate over a long distance, as you would if you wanted to detect something from far away with a radar or communicate with somebody far away, that's a more valuable band to you. You need less power to achieve the same link. Now, how valuable is valuable? So there were two recent auctions. Congress declared we need to make 5G happen, and the bill was called like the Beat China in 5G Act, something like that. So they were motivated to beat China in 5G, and industry said, well, we need more spectrum to do that. So initially, the spectrum was owned entirely by the United States government within the US and its possessions. And then they decide how that spectrum is allocated and given out to industry and shared. So they decided here in these bands, only DoD is using it. It was allocated only to federal use, but they're really not using it as much as telecom would. So let's auction up for both people to exist. So you have your incumbent, and I'm going to talk mostly about the Navy. And then you have those who paid money to be second-tier users of these bands. So across these two auctions, they gave up 250 megahertz of flexible use spectrum, and industry paid $27 billion for that 250 megahertz, not even just to have it, to be the second-tier users. And that is prime spectrum, but you can think there's trillions of dollars of spectrum just in the L and S bands. Now, as part of that, DoD assessed, well, you can't just show up and everybody's going to get along and we won't be interfered with. And the rules of this band are shall not interfere with the incumbent. So we have work to do to make sure that you don't interfere with us. And they assessed that overall adjusting to just the first of those two bands would cost $13.5 billion of studies, realignments, upgrades. And if you zoom in kind of to the center of the chart, you'll see that 12 million of that is the Navy. So, excuse me, 12 billion of that is the Navy. So the Navy was the most heavily impacted by this band auction. And that's because they have systems in that band. And unfortunately, they have systems in that band that are near priority markets like cities. Cities tend to be near coasts, which is also where Navy ships are. So I want to motivate, why does the DoD need all this bandwidth? Because one suggestion is, hey, this is prime real estate. You're not using as much as we would. Why don't you compress? So I have a couple of things here. And by the way, everything you see in this presentation is from the open internet. Over on the left, you have this chart about how increased bandwidth gives you better range and angular resolution in your radar and allows you to go from, hey, there's something at this distance to, hey, there's something in this distance and it looks like this, and it looks like a missile, and it looks like that part of the missile is actually the seeker or the reentry vehicle or whatever part we actually want to shoot. So you can probably understand why that's an important problem for them. In the top right, we have a nice graphic of a jamming device. So if you were trying to perform your radar operations and somebody has a broadband jammer, you're going to look over there and all you're going to see is noise coming back. If it's a reasonably powered jammer, the signal coming from it is going to be much higher than the reflected signal of the targets you're trying to see, and you can't see them. One of the reasons that your radar needs more bandwidth is because it can change channels rapidly. And if you're changing channels rapidly in a pseudo-random fashion, they can't predict what part of the band you're going to be using at any given time to perform that detection. And to continue to jam you, they have to spread out the frequency that they're jamming, which reduces the power in each frequency. So frequency agility is another need for the DoD. And finally, DoD needs a lot of bandwidth because they have hundreds of spectrum-dependent systems crammed all up together on the top of the ship. And the only way that they can all survive together is by using different frequencies. Now, I don't have nearly so much to talk about here. If you're interested in why industry needs bandwidth, I know Dr. Tripathi and Dr. Reed have a book out on 5G. You can talk to any of the cell system guys. You can probably talk to Dr. Dietrich about this, and they can all give you a much more in-depth answer than me. But I'll refer again to the seemingly exponential growth in traffic and our capacity law again. You need more bandwidth, you need more signal-to-noise ratio. So why not just signal-to-noise ratio? You can improve your signal-to-noise ratio by deploying more smaller cells, and those are called microcells. And there's a lot of applications where that's good. Like here in Arlington, we have a city where there are a lot of people needing a lot of traffic, and you can deploy these small cells all over the place, and it works out really well. And actually, there are really interesting studies on small cell propagations done somewhat recently down at Blacksburg. If anybody's interested, I'll try and find that for you. But it doesn't work well for, say, like a rural area. You're not going to deploy, as a telecom company, you're not going to deploy a small cell out of everybody's house in rural Oklahoma. You're going to put up a big, loud tower that's going to cover broad swaths of region. Also, the more power you're using, the more operating costs there are. Another reason they need good signal-to-noise ratio, my bottom right, you see 64-bit and 256-bit QAM constellations. These are two different ways of encoding data, and 256-bit QAM is able to transfer more information per unit of time than 64-bit QAM. I think that's self-evident. But you need good signal-to-noise ratio because as you propagate over the air, your constellation here starts experiencing amplitude noise from propagation and phase noise from propagation, and results in this constellation getting fuzzy. And that's how you get bit errors. So the more signal and noise ratio you have, the more distinct each symbol of the constellation is, and the higher n bit QAM you can get away with. Now we're going to talk about spectrum sharing policy, which you'd be surprised how close you guys are to it, especially here at Virginia Tech. The wireless group here and the NSI and Hume Center and all of these people actually work very closely with a lot of the policymakers. And I'll say, as somebody who's not that far out of school, I'm shocked by how close I am to the policy also, and how close the engineering is to the policy and how much policy you have to know about. So again, here in the US, if you want to access the spectrum, if you're a federal user, you go through the NTIA. If you're a non-federal user, you go to the FCC. I support federal users, so we're going to talk about the NTIA. But if you are out to make a product as a commercial entity that wants to access the spectrum and transmit in the spectrum, you need to go through the FCC and FCC ID. And I think that process is probably a lot like the NTIA one that we're going to talk about. So the NTIA has the NTIA Red Book, or that other long name. It's 850 pages of policy guidance that you have to know if you want to work in the spectrum. So every single system on that Navy ship we talked about, every wireless router that is deployed onto a Navy ship, every communication system, they all have to be approved to play nicely in the spectrum and not cause undue interference, and to be reasonably resilient against interference themselves. So to access spectrum for the DoD, there's a whole lot of steps. When you hear about, hey, the Navy's building this new thing, and it'll be deployed in approximately 15 years, this is one of the many reasons why. First thing you want to do is say, hey, our engineers would really like to build this, I'll say, 1 gigahertz fundamental radar. Well, you have to go and look at the table of allocation, which is the big ugly table I showed you about, and say, am I allowed to do radio determination in that band? If not, then it'll be illegal for me to transmit. So you have to make sure that you conform to the table allocation. If you're going to send the system to other friendly countries, you have to make sure that you're following all of their laws also. And you have to make sure it's going to play nicely with everything around where you're going to deploy it. So if it goes on something like a ship, you'll do a co-site analysis. And we'll talk about that a little bit more later. So once you've decided, yes, this is something that's going to be within the realm of reason to do, you start building it, you do all the engineering, and you start talking to NTIA and say, hey, I want to get the frequency allocation. And this is saying your class of system is allowed to exist. So that involves testing to make sure it adheres to all the guidelines set out in the Red Book, and making sure that you adequately describe what your system does so that other people can make sure they understand it when they are doing their spectrum applications. And then finally, if you want to have a specific instance of that class operate in the spectrum, you need a frequency assignment, which is typically done by local folks. If you're on a DoD base, there's going to be somebody who's called the spectrum manager, and they have a list of all the things that are operating, and they grant you an assignment. So not thrilling, I know, but there's a lot of really cool field work that goes into making sure that things are actually adhering to these rules, and a lot of testing that goes into the development process to make sure that you are likely to adhere and prove that you are. But now I'm going to back up to sharing with not the DoD. How do you share spectrum? There are 3 ways: space, time, and frequency. And then I have to caveat it because there are other things like CDMA and telecom, which again, you can ask your cell systems professors about. What I mean is there's only 3 ways without other communications, like, hey, this is going to be what we're doing. So spectrum sharing in space is reasonably obvious. If I have, say over on my left side, something that needs radio quiet, I put it somewhere and I tell everybody else to go away. So that seems pretty easy, but you're depriving people of all that space. So naturally, when that radio quiet zone is put up, if that red square there had extended to Washington, D.C., people would say, well, hang on, there's a lot of people who live in D.C. who would like to be using the spectrum. Are we sure that the zone needs to be that large? So you try and constrain the space that you keep everybody away from by the best model you can make. And one way you might do that is to take your freeze equation and take all the possible interferers and model the expected interference at your sensitive system and figure out if it's above your sensitivity threshold. But that's very, very reliant on having a good model. And it's very hard to model propagation very, very accurately because it's a very random process. You have all kinds of vagaries from atmosphere changes. The ionosphere can be very relevant to your propagation gains and losses. There's an effect called ducting, wherein you bounce off of different temperature layers of the atmosphere and therefore different density layers of the atmosphere. And you can propagate actually far, far further than you think. And you actually, your power falls off at 1/r less than 2. So you may get a lot more interference than you think, or on rainy, hazy days, you might be just fine to actually have your interferer closer to the sensitive instrumentation because you have a lot of water absorption. Sharing frequency is fairly obvious. I'll be in this channel, you be in that channel, and we'll be fine. And that's all well and good if you actually stay in your channel. In the NTIA Red Book, depending on what type of station you are, what band you're in, there are different rules for how much out-of-band emissions you're allowed to emit. If you meet those requirements, then you're allowed to emit. But people next to you in frequency may not have the ability to reject as much out-of-band interference as maybe they should. And so that can cause problems. So back in, I think 2020, when I was starting to do my master's here, there was a big discussion about, hey, you guys want to do 5G over here and 3.7 gigs, but our radio altimeters that we put on the belly of all of our airplanes in the US, we operate, 400 megahertz away from you, but your power is so high that your out-of-bands emissions are still going to knock us dead. And this chart over here on the right, the dotted green line is the mask of their bandpass filters, which is really quite wide. And at the time in Dr. Reed's cell class, we had a debate about, hey, I'm playing FAA and you're playing FCC. And the conclusion we came to was, well, guys, you can tighten up your filters and then we won't have such a problem here. The sharing frequency is good if you coordinate what frequencies everybody's going to use and if you have a secure channel to coordinate that. And then the most interesting one, spectrum sharing and time. Kurt Schabach of Federated Wireless, who's another VT alum, gave this talk about CBRS band last year. And I recommend if you are interested in spectrum sharing, go back onto YouTube and search for his name at Virginia Tech and you'll find his talk. It was very, very good. CBRS is one of those two bands we talked about that went for some, I think it was $25 billion. And they share in time. Again, Navy most heavily impacted systems, $12 billion to deal with the new secondary users. The way that this spectrum sharing in time works is the Navy ship is going to be either in port or on the coast. And if it's further away, then you're sharing in space and it's no longer a problem. For this band, the way that secondary users are granted access is they have to go to a scheduler called a SAS, a Spectrum Access System, and ask, hey, may I use this band? And the SAS goes and it looks for a Navy incumbent and it says, yes, the Navy incumbent is there, or no, they are not. And if they are not, you can use the band. If the Navy incumbent is there, and they figured this out by deploying sensors all along the coast, and these dynamic protection areas are all over the US and possession coasts, and they decide, yes, the incumbent is there based on some very high level parameters of what our waveforms look like. They assess that they're there and they have to shut off all of the secondary users in a really quite large radius for some period of time until the incumbent goes away. So you can probably imagine that can get quite contentious. This is one dynamic protection area. It's the real one. And you see when the Navy ship is operating in that DPA, we shut down from close to Providence, Rhode Island to looks like Philadelphia gets hit. So that's 100 megahertz of spectrum that New York, Philadelphia, New Jersey, Long Island, all these people can't use that band. It's a really, really big impact to these new secondary users. So much like sharing space where we said, let's try and keep that geographic space as constrained as we can. The Navy wants to operate free of interference, but they also want telecom to be able to get as much out of their $25 billion as they can. So there's a lot of studies with respect to propagation and actual sensitivities of Navy systems and the like that goes into making the sharing methodology as efficient as we possibly can. So the long-term goal of spectrum sharing is to fill all this white space. If you work in RF, you're probably familiar with looking at a waterfall. So this is a 3D plot. The x-axis is our frequency, y is time, where the nearest section of time is at the bottom of the screen, and the colors are intensity, where blue means there's nothing there really, and the closer you get to red, the more intense the signal is. So this is a lot like looking at an aerial view of a human population. You see in the left to center there, we have a very, very active region that can be likened kind of to a city. Off to the right, you have these scattered uses of spectrum that's more like the suburbs. And then off on the left or the right, it's kind of like looking at cornfields. There's seemingly nothing going on there. So the goal is, this is not an effective use of spectrum, right? All that stuff on the left and the right, why can't we fill that up? And going back to my metaphor, well, you still need somewhere to grow corn. If this is the Navy spectrum, it might look like they're not using it right now, but it's there for a good reason. And it may not be efficient, but sometimes a mission is important enough that inefficiencies are acceptable, but also we need somewhere to put all these people. So there's that trade-off, trying to decide how can we protect our mission critical systems while still enabling ourselves to make efficient use of this very limited resource. Over on the right, the problem makes me think of a Maxwell's demon a little bit. If you have done any thermo, it's how do we fill this white space? So this portion a little bit to the right of center, you see there is a lot of white space there in between these kind of spotty emissions, but to be able to know that that space is going to be there requires a lot of coordination. And if you want to do really, really tightly packed efficient spectrum sharing across a broad band, you need to solve for where the white space is going to be and solve for that schedule on the order of sub-milliseconds. And it's a big computational problem. If you're interested in the problem, at least the way I look at it, it's called the bin packing problem, which is if you go to this supposed scheduler and say, hey, I need to transmit this much data, well, we can fit that data into the frequency domain and the time domain and make our box. And so the scheduler will decide, hey, you get this much bandwidth in this much time. So they decide the parameters of the box, and they have to pack all of these boxes together. And I don't remember the big O complexity of that problem, but it's bad. So wanting to do it for all of these millions of devices that are accessing the spectrum is going to require a lot of compute power, as well as the real killer, a lot of understanding of the actual propagation environment. Because this is a really nice picture, but you never know if you're going to actually transmit over to the next scheduler's domain more than you think. Now, we're going to talk a little bit about electromagnetic compatibility, which is not destroying your own stuff with your transmissions. So this is a semi-helpful chart, covers what is EMC. But at the end of the day, it's, if you think back to your picture of the Navy ship with all of those systems, we can coordinate in space, we can coordinate in time and frequency, but there's all kinds of unexpected emissions. EMC is looking at coupled signals that will induce voltages onto things like waveguide and lines and all over the place. It's also looking at things like, okay, our fundamentals are far apart, but am I going to have spurious emissions coming out of my loud transmitter that's going to ruin the sensitive receivers nearby, even though they're well out of band? Or am I going to have a large harmonic coming out of my transmitter? It's just making sure that everything that's co-sited gets along well. And there's my picture again. So you can picture, even though a lot of these systems are far from each other in frequency, we don't live in the engineering world, we live in the real world, and they're noisy. And you can saturate things that are well out of band by having sufficiently high powers. You don't have good roll off and you don't have good out of band rejection. So there is a whole lot of work that goes into the design of these sorts of sites that you see on the top of the Navy ship to make sure that everything can coexist. On the left, we have a picture of a radar that is experiencing interference from what I don't know. In the Navy, if you experience interference on a radar while a missile is coming over the horizon, you die. So that's not good. In telecom, if you experience interference, then you have to jump to another band to get your data across, and that can be bad too. That sometimes things are a little more life and death than getting to download speeds. So that's one of the arguments for why the Navy really likes its bandwidth and will tend to be more conservative to their own side when they're figuring out how to share properly. This is, again, from our NTIA Red Book, which if you really do care about RF engineering, you're going to have to learn how to use as a source eventually. And it's really decently well put together for such a large document. But it defines some things like, if I am operating this station class, and I'm operating in the US, or if I'm operating in international waters, here is how my system has to behave. We have our in-band emissions, which are part of the normal course of operation, and then it defines things like how far away from your fundamental can your minus 40 dB limit be, or how high can your spurious emissions be. So you have to make sure when you're building a system that you conform to these things. And we go out into the field and we do a lot of testing in support of people who are developing their systems to ensure that they conform to these criteria. There's also an interesting subsection of EMC called integrated topside design, which is essentially just a way of saying, make sure that we all get along both in the electromagnetic domain and acoustically, power-wise, everything. So if you're more of a modeling and simulation type person, and you're interested in this sort of work, then that is what you'd be looking at. And this is a type of tool that we sometimes use for over-the-air testing. Has anybody worked in an anechoic chamber? So this is the closest thing you're ever going to see to engineering world, but with real-world systems. If we want to go from our model and simulation results of what our emissions look like, or what the reflectivity of the system looks like, if you can help it, you don't just jump straight onto the field where you have crazy multipath and who knows what you're actually going to be measuring and whether that's really a good test of your emissions. You can throw it into an anechoic chamber. That means no echoes. In this case, it means in the RF domain. So at Dahlgren, we have a lot of really cool anechoic chambers. This is not one of ours. But you see this blue all over all of the surfaces. This is a particular type of foam that absorbs all incident RF energy within certain bands, and it's generally pretty broadband, and it turns it into heat. So you don't get any reflections, no multipath, and you can go in and you know that you are just looking at the direct path signal of the thing that is under test. And coincidentally, in this picture, I don't know what this test is, but another reason you'll want to go and look at something in an anechoic chamber is to establish the radar cross-section of a device. If you have a target like this, you want to have really good data on what its reflectivity looks like from different aspect angles. And to do that, you have to make sure that you're not getting multipath. Then radiation hazards, or RADHAZ, is another very important study that you should perform whenever you are building a spectrum-dependent system or operating in an RF environment. And its radiation hazards, hazardous effects of radiation to ordnance, personnel, and fuel. I didn't review really well on the exact details, but over on the left is a simulated picture of an event that happened, I think, in the 60s, where a helicopter landed on the flight deck of an aircraft carrier, and one of the high power systems there accidentally triggered and initiated a missile on the helicopter. And the missile went off and exploded and caused a big fire and killed a bunch of folks. And this was all because it landed in too high of an electric field. A lot of explosives, certainly at that time, and I think probably still today, I'm not an explosives guy, have what's called an electrically initiated device. Here, this middle picture, and it's just a spark gap. When you are trying to cause it to go off, you induce a voltage across that gap, and there's breakdown between those two terminals, and that starts off your chemical reaction. And you can induce a voltage on those two lines through radiated energy, not just conducted energy. So you have to look at, hey, I've got my radars here. How far do I have to keep all my explosives away? Much like these spark gaps in the middle, humans have dielectric materials that are very conducive to breakdown between them, namely the eyes. If you get too close to a high power system, you can go blind because you induce thermal effects from large voltage being applied across your eyeballs. So there are, even though this is in some cases non-ionizing radiation, there are still safety standoffs that you have to take from high power systems. And again, that's all subject to a good idea of your environment. So if you're on a ship deck, it's not like working on a plane. You don't have nice, clean radiation patterns. You'll get all kinds of multipath, and you can get hotspots from buildup from the multipath that get even higher than you would normally think. And I put this slide on to talk about EMP protection. This isn't so much a question of sharing, but it's still an RF concern to think about. Back when I worked for the Navy, I was actually working in directed energy systems. And they have a motto over there that everything in the world is actually an antenna, just most of them are bad ones. But any amount of bad antenna gain can be overcome by more power. So when you're designing something critical like a ship, there are ways of generating broadband, high power pulses of electromagnetic energy. In this case, on the figure on the right, it's a detonation of a nuclear weapon that causes the electromagnetic waves by gamma waves interacting with the ionosphere. And that will cause broadband high power energy that can couple into not just your antennas, which you call a front door attack with backdoor attacks. Everything is an antenna, even if it's a bad one. Doors, HVAC ducts, all these things look like really good antennas if you're high enough power. So I'm going to talk about a little bit of research needs real quick, and then we'll see what time it is. In October 2024, the National Spectrum Research and Development Plan was released, and it guides government support for spectrum-related research. And what that should mean to you guys as people who may be about to pick out your research topics and who may be going on to PhDs, this means this plan tells you what the government is going to spend money on and what you can say you want to do and get money. So highest priority research accelerators, public data sets. In the RF world, you can never have enough data. Also test beds and testing frameworks. For these two things here at Virginia Tech, I know that Dr. Dietrich was working on these really cool things where he was strapping SDRs to drones and flying them around to collect data. If you guys are interested in that, I'd reach out to him. I also know that there's a large network of SDRs set up down in Blacksburg. Sorry, I forget the name. I am sure that somebody online could let you know how to get involved with those efforts if you're interested. And the TRL pipeline review is more of a government thing. Researcher rotations into regulatory organizations that I would pay attention to. Having worked in supporting the government for some amount of time now, I will tell you that Congress decides how much money goes to the DoD, and eventually it gets down to us. And there are many people in between us and them, and they can't spell RF. Having informed people with engineering backgrounds, not necessarily in regulatory organizations, but able to support them is crucial to making good decisions. It might be that if it were better communicated that it would cost the Navy $13 billion to even share a band, there would be some more consideration about whether or not that band is suitable for auction. Or it might be that we were better able to focus the research into effective methods of sharing. Not that anything's going wrong right now, but it's always good to have people with technical backgrounds making policy decisions. There's a lot of cases where that isn't happening, and it's unfortunate. So Kathleen, how much time do we have left? Because I have backup slides that we can move to questions.
For a question and then see.
Yeah, sure. So we'll go to questions. The rest of my slides are just different points from that National Spectrum Research and Design Plan. So if you guys are interested, we can talk about that. But
So let's open the floor for questions. On the Zoom, if you have any questions, please write in the chat. Any questions from here?
Does anybody here work in RF? Electromagnetism, radars, communication systems? Anybody involved in this group?
Maybe
Sure.
What is the coordination? How is that? Like, have a private company. What do I do?
So if you're a private company and you want to use the spectrum, how do you coordinate between federal use and private use was part of the question. If you're not building the system, you'll just go buy it and it'll already have an FCC ID and be approved, and that work will have been done for you. If you're a private company wanting to develop a spectrum-dependent system, you'll have to go through the FCC process, and that coordination will happen. Use in what manner?
For example, let me make it simple. Let's say that I am a wireless internet service provider.
Okay, wireless internet service provider.
Yes.
Sorry, here, I'll give you.
Yes. Let's say that I am a wireless service internet provider, okay? And I want to provide internet to maybe Department of Defense and maybe not. But the spectrum may interfere with the Department of Defense. So how is that going to work? Can you give us like an idea? Is that simple? Is that something competitive? Is it, you know?
Sure. So if you are trying to provide wireless ISP, you have to look into, well, again, if you're not making the equipment, if you're merely providing it, then that process will have been done for you. And in terms of spectrum coordination, there's nothing for you that you have to do unless you're wanting to install it on the base or whatever, in which case there's a spectrum management coordination, but generally that would be handled internally. If you are trying to create a new system, the wireless ISP would fall into the station class of fixed mobile. Losing track of the exact class. But these bands that have been recently put out for auction, I would speculate that one of the things telecom is hoping to do is to do wireless ISP in those bands, which is why there's very interested in it, because the cell traffic is really, I would say by my estimation, in many markets doesn't require these channels. They already have many others. But if you're trying to do fixed broadband, you need to figure out what frequencies are allocated for that use. And then if you were a federal entity, you would go through all these steps, the SSRA, getting a 1494. As the FCC, I imagine you have the same sorts of constraints about you have to have this sort of roll-off and out-of-band emissions. There are limits to the amount of power you can put out. For example, in these bands that we've talked about, there are limits of EIRP, so effective isotropic radiated power, which is the amount of energy outside at the face of the antenna. They're limited at plus 78 decibel milliwatts. And those limits are not just for interference concerns, but also you don't want to create too much of an electric field and have these like herp concerns with people's eyeballs and such. But if you're just looking to take an already existing device and provide it as a service, you are not in charge of the coordination.
Okay, I have two questions from two Zoom guests. So the first one, Does V2X have any relation to the vehicle to everything con?
No,
Okay.
the people who chose that name aren't engineers. So when we found out that we were becoming V2X, we all said that, and it's not that.
Okay.
That's the whole answer.
Okay. All right. The next question from another guest. Thanks for the presentation. I am an AI engineer working on RF, space systems, and communication systems in the defense space. When it comes to collaborating with defense technology companies, for example, startups focusing on government contracts, does V2X subcontract or partner with non-traditionals? If so, what does that process look like?
Partnering process, I don't know I'm the right person to talk to you, but I would be very, very willing to have a follow-up conversation if we can get your contact information. And I'll throw out a disclaimer here. If you are, unfortunately, I have to say, if you're a US citizen and you're interested in working in the RF field, I'd be happy to talk to you. We are always looking for talented individuals and would love to talk. I'm going to use that question as an opportunity to talk about machine learning in RF spectrum. If you're interested in that, this is an amazing school for it. I got interested in this field by stumbling across a paper from another alum who's founded a company up here in Arlington called DeepSig, where they're looking at machine learning for spectrum tasks. When you look at this picture here of this RF waterfall, you don't know what any of this stuff is. You haven't seen it before. It all just looks like power to you. And if you are an operator on a Navy ship looking at the RF spectrum and something pops up, you don't know what it is. That might be your radar. It might be something hostile. It's hard to tell. And it's going to take you a human time scale to assess the situation. And in many cases, that is not fast enough. In the case of the DoD, it might be because there's a threat coming very, very quickly. And you need some guidance to detecting what's in the system, in the environment. In the case of something like a spectrum sharing scheduler, you may need to detect whether there are stray emissions from who knows what and classify it. One of the very active areas of machine learning in the RF spectrum research is classification of signals. Everything I talked about there. So known systems, you can do things like supervised learning, where you go and take it into the laboratory and collect a bunch of data, and you say, this is the system. And then when it shows up again, you know, hey, that's this system. And if it's behaving slightly strangely, you might be able to say, hey, this system maybe needs some maintenance, or I told this system to do one thing and it doesn't appear to be doing that. But there's also very, very compelling work in, hey, I don't know what this system is, and I sure would like to learn about it. In the DoD, that would be the field of ELINT or SIGINT, signals intelligence or electronics intelligence, going out into the world and seeing something new and learning as much as you can about it. Commercial applications, I couldn't speak to as much, but certainly if you're interested in the machine learning aspect of RF, there's a world of funding out there, definitely in the Northern Virginia area and surely in Blacksburg. So that's a great field to be in. All right, I can't see online questions. Are there? Yes.
Quick question. If I heard you correctly, I think you briefly mentioned that the RF group was strapping test equipment onto drones and doing some research with that. Is it here to elaborate?
Oh, that's as much as I know about it. Dr. Carl Dietrich was doing that. And I don't know any more than that. But he was taking software-defined radios, SDRs, and I believe attaching them to like Mavic drones. And I'm sure if you follow up with him, he'd be happy to tell you more. Kathleen, do we have any other online questions?
Okay. I was wondering if you had any advice given your recent experiences in getting the Master of Engineering while working. This is a very informative presentation.
Absolutely. So there we go. I thought I was going to do a PhD in physics for the longest time. My undergraduate degree was in physics. I did not go right into grad school after undergrad because I didn't have any money. I started working and I thought, boy, this is nice having money. And by the time I had enough money to start thinking about going back to school, I realized that I didn't want to not have money again. So how do I do a physics degree part-time living in fairly rural Dahlgren, Virginia? Well, you don't. But Virginia Tech has an engineering degree that you can do part-time already virtually. This was 2019. I was looking at it, and the whole world hadn't gone virtual yet. But Virginia Tech already had done so for this program. And so I landed on that. And I was very, very happy with that choice. I thought this was a wonderful school. Doing the work remotely part-time, I took 3 credits my first semester and then 6 every semester after that. I think I needed 32 credits total. So I got it done in 5 semesters. And you don't have a weekend anymore. That's at the door. You're doing homework. But it's really not that long a period of time. And I don't want to say that there was any financial reward for it at work. I kind of already was where I was, but I learned a ton that was very relevant to my work. I don't think I would have felt as competent in my field without having done it. It was a really good experience. You get to know a lot more of the people, and RF is a very, very small field. I can't tell you how many times I looked at a paper and say, hey, I know that guy, they work, this is a Virginia Tech guy, or this is a guy up in MITRE in Northern Virginia, or Paraton in Northern Virginia. It's a very, very small community. And if you're up here in Arlington, you're very close to it. Probably that is true as well at Blacksburg. So the kind of human engineering aspect of it was very good too. Get to know folks. And I found it, if you can commit a little bit of time to it, then it's very much worth your while. I didn't go for the PhD though. I had thought about it, and I took a semester off in between and couldn't make myself go back. But if you have it in you, which I didn't, I would suggest that too. All right, any other questions? All right, thank you guys all very much for your time.
Appreciate it. Thank you.